Well, it's a real pleasure to be here today, and I'm honored to be part of this symposium as well. It truly is about Harry Wasserman, and as a colleague of his for a number of years, 13 years at Yale, it was just a tremendous pleasure to be here in that time, and so just honored to be here. It's also fun to be able to tell people a little bit about some of the work that we've been up to, and you're going to see it kind of span quite a number of years today, which I'll talk about. Now, I don't have any pictures of Harry. I was in many places around the world with him, and I have a few pictures, but they're from far away. So I wasn't happy with any of the thousands that I looked through. If I were Marty Saunders, there would probably be tens of thousands of pictures. But I didn't have any that I could put up there. And so, you know, I thought I'd have to do an imitation of Harry. So I'll do an imitation. I'm going to preface this by saying I got here in 1993. My office was in the hallway right out here where the fishbowl for Kingston's theoretical chemistry practice. All the teaching still took place in 160 and 110 typically, the large lectures. And Fred Ziegler and Mike McBride were lecturing the sophomore classes at that time. And so they would walk by my office to go to class, and they would always wear a tie when they were teaching. And so I thought, okay, well, I have to get with the program. When I teach sophomore organic, I need to wear a tie. And I'll tell you, I've never given an organic lecture to undergraduates without a tie on. So oftentimes, unlike today, I would be dressed a little bit like I am now. And of course, you know, Harry Wasserman was here in the hall. And I would encounter him a lot. And more often than not, when I encountered Harry, when I'm dressed like I am now, Harry would, you know, that was it. Now, as an assistant professor, your resting state is hyper-paranoid. And so, of course, I thought, I don't know how to do something wrong, you know, with this. And I kept trying and trying and trying. And no matter, you know, I'd work on it at home. But if I get to work and see Harry, it'd be, you know, this. And it was, you know, after the paranoia subsides a little bit, you realize that this is a gesture. He's telling you that he cares about you. And that's fantastic. He not only cares about me, he cares about his colleagues, other colleagues, his students, pretty much everybody. And what a great thing to do. It by kind of osmosis just generated an environment that was good to work in, especially when you're in this hyper-paranoid state. You know, there are people out there, your senior colleagues, that actually care about you. And that was Harry Wasserman. That one gesture kind of represents an awful lot. So, I'm going to get right to the science. And I'll talk fast, but I have lots of summary slides so that, you know, become clearer, you know, periodically throughout this talk where I am. I'm going to talk about natural product synthesis. This is a molecule, actually, I'm going to talk about today that we started, I think, in 1997. So actually, a lot of the faculty here have already sat on thesis exams where some of this work has been presented, so they'll see it again. And some of it may be familiar, they'll have forgotten it, I hope, you know, so it looks like it's going away. But I wanted to tell this story because it spanned kind of so many generations, and that's what I'm talking about. It'll be a synthesis directed towards the phomoidrides. Now, it's funny. You know, since I started, I've always had to be kind of making the case for synthesis, natural product synthesis. Why do people want to do natural product synthesis? I was just at months ago, at a ACS regional meeting in California. And an assistant professor from the West Coast told me that I should not be talking about the synthesis of complex natural products. I should be talking about the synthesis of secondary metabolites. Because it sounds so much more interesting, you know, than natural products. So, you know, I immediately changed my slide. The synthesis of secondary metabolites. Not really. But I did change it just for fun in that symposium. It was kind of fun to talk about it, so I put it in this one too. But it kind of represents a little bit of a struggle that I've always had with natural product synthesis and kind of trying to make the case. The reality is, this has been a long-standing struggle. People were struggling with making the case for synthesis long before I started in my independent career here. And there's evidence of this in the literature. So here's a volume, the Robert A. Welch Foundation. So this is the proceedings of the Welch Foundation. Of course, It's not really the literature that you'll probably go to. You might be able to find it in the Sterling Library, but I kind of doubt it. I got this actually on eBay for $4.95. So, but they're beautiful compilations. And so every year the Welch Foundation holds a conference, and in 1969 or 68 there was one devoted to synthetic chemistry. And in this conference, the person that was giving the opening remarks was R.B. Woodward. His opening remarks are detailed in this proceedings. There's also interesting things like they will detail the questions and answers at the end of their compilations of these proceedings. Name who was asking the question. So you can see some interesting questions asked by people. But nonetheless, Woodward was giving the opening remarks of this conference somewhat off the cuff. And so I'll take a few quotes out of these opening remarks out of this book. And Woodward was saying, I'll say a few things more or less off the cuff. I really wish I could speak like this off the cuff. About the field of organic synthesis. I fell in love with the field as a small boy, and the affair is still going on. I remember that Harry was Woodward's first graduate student. And as far as I'm concerned, we could leave it at that. So he was content just with doing synthesis because he loved to do it. He says, but there are more analytical types about it who occasionally try to think about the general state of it or condition of it. For example, one hears sometimes remarks of the following sort. Well, now, you've shown that anything can be synthesized, so the field is happy. This is 1968. Little did I know I was getting into this field that already had it, 20 years before or something like that. So what would you want to say? Well, in the age in which there's very severe competition in reaching the height of absurdity, in remarks, that comes pretty near to taking a blue ribbon. Who knew that age was going to last until 2015? We're still here with people saying sorts of things. And Woodward went on to say, chemical synthesis always has some element of planning, and this is one of my favorite parts of the opening remarks. But the planning should never be too rigid. He kind of is acknowledging in a way that, synthesis is not something that you can just plan and carry out, and it's going to work out the way you plan it. The planning can't be too rigid. You're going to have to make changes as you go along. And he went on to say that the specific objective of the synthetic chemistry is the excuser's activity. Really, a nice way of saying the target you're trying to make is often not of special importance in the general sense. Rather, the important things are those that you find out in the course of your research. That was true about synthesis in 1968. It's certainly true about synthesis today. It's really all about the things you kind of encounter and find out while you're working through these problems. So I'll tell you about another way of representing them. That it was an interesting paper on Gavant years ago. And you can kind of sum up these things by what people believe is that you take a target molecule and you work the magic of retrosynthetic analysis on it, and out pops the starting materials. And then lo and behold, you put those starting materials in the beginning, and out pops the product with the same ideas. And oftentimes, that's how we write the paper. So we do this to ourselves in a way we bring on this criticism. And it's something to be avoided. So generally in the talks I try to give, I paint a better picture of what goes on in our laboratory, which is kind of like the crossed arrows that Brian was showing in his first slide, where we don't kind of really know what we're doing. We start out with some ideas, but invariably we encounter these problems. We go on to other ideas. Maybe at the end of the day, we'll make one of these targets. So this is the landscape that the student has to look forward into my group. It's not very long before they realize that I don't have any idea how to plan a synthesis from beginning to end. And it's really up to them at some point early on in their stay to start taking on ownership of this project and working through these problems, hoping to get to this target. But in reality, this is where all the learning takes place. This is where you discover new things, and where the students really become excellent problem solvers. Chemical problems. So I'm going to tell you about the Phomoidrides. The Phomoidrides are shown on this slide. They were isolated at Pfizer, just up the road, in the mid-90s, 1997, 1996, when Pfizer still had a natural products group. Now, if Pfizer would have called it a secondary metabolite group, it might still have that group. I'm not sure, but it might be worth a try. They can check it out. But it was found some extract from a fungus that was found growing on the juniper bush in Dripping Springs, Texas, which actually is not too far from where I'm living now. And growing up in Colorado, I never thought I was going to be living anywhere near Dripping Springs, Texas. That's where it was found. We've been working on these compounds since about 1997 or 1998. You can see there are a number of nice syntheses that have been published in the past, but that didn't deter us from continuing to work on this molecule over the years. I'll tell you a little bit about that today. In addition to phomoidrides A and B, C and D were isolated a little bit later by Gary Sulakowski. So this is the whole family of the phomoidrides. You can see that these compounds differ. The first two isolated congeners, they differ by the condensation reaction moving to the right. So kind of hemiacetals and acetals, you might call it that. From top to bottom, you're looking at a stereochemical change at this ephemerizable stereocenter, and those compare to A and B compared to C and D as being diastereomers. Okay. Now, one of the interesting things, we always kind of are looking at molecules, what's challenging us in these molecules? There are plenty of things that challenge us in these molecules. The core structure is interesting, a bicyclodecadiene with a bridgehead olefin in it, an interesting structure to make. Brian spent some time talking about all carbon quaternary centers, and so this molecule certainly has one of those embedded in this core structure, and that was going to be a challenging feature to make. If you look at the Nicolau synthesis, you can almost attribute 20 steps of that synthesis to try to orchestrate the introduction of this quaternary center. So it was a challenge that was going to be facing us. The bridgehead olefin would be interesting to introduce. The spiroacetal, unusual in natural products. This ephemerized the stereocenter, it's some olefins in the side chain, and then the maleic anhydride at the top, which kind of hydrolyzed olefin. Something we would need to introduce perhaps late in the synthesis. So how do we look at this molecule in 1998? Well, as Fred had alluded to, Brian had been working on staurosporin in the lab, K252A. One of the key components in the synthesis was a Claisen rearrangement that we had done to generate some of the starting materials. And so we were doing Claisen chemistry in the lab. And as often is the case, ongoing chemistry is going to influence the thinking of other projects. And when we looked at the structure of the phomoidrides, Joan Yargerson actually in particular, Brian was still in the lab at the time when we started thinking about this, they were coming up with 3,3 sigmatropic rearrangement ideas as a way of maybe introducing this 1,5-diene portion of the molecule. And so we were applying that sort of disconnection and thinking about those types of reactions as a way of assembling this ring system. And so the next thing that you do in this process is you go to the literature and find out, okay, what's known about these sorts of reactions? Certainly Leo Paquette must have done this cope reaction at some point, in his career. And we just could not find anything very useful about those sorts of cope reactions. And so we decided to make a quick model system. Joan built this model system here and showed that, well, you could get it to do a cope reaction. These are anion accelerated conditions. He's having to heat it up. So this is looking like it's not the easiest cope reaction in the world to do. So we were a little bit hesitant about this. And Joan made a little bit more hindered compound and found this compound did not want to rearrange at all. And it turns out that at the time, we were not the only ones thinking about cope chemistry in this field. Derek Clyde, working in Alberta, and Jim Layton, working at Columbia, was also thinking about doing cope chemistry in order to install this bicyclic ring system at the core of the phomoidride. And they were finding that this was a pretty tough cope reaction to do. They had to incorporate some strain into the molecule in the form of this butenolide, expose it still to some fairly high temperatures, 1,2-dichlorobenzene, in order to get this reaction going. But we didn't abandon this idea before that. We thought we should be thinking about something else. And so Joan was up one of these brick walls in the process. And so what do you do with this? Well, Joan reassessed where he was in the synthesis. He wanted to do a cope reaction, which was going to form this bond and then break the bond here to generate the bicyclic system. And Joan simply asked the question, could he do a synthesis where he formed that bond initially, and then in a later stage did the breaking of the carbon-carbon bond? And so now the strategy changes from a 3,3 sigmatropic strategy to one that's going to be a fragmentation strategy. And I think fragmentation, sometimes when you see syntheses done with fragmentation, you think, wow, how did they think of that idea? That's really cool. And we weren't smart enough to see a fragmentation right off the bat here either. This kind of evolved over a period of time, thinking about kind of an obvious disconnection first, and that led us to this fragmentation reaction that we began to think about. So we began to wonder about the feasibility of those sorts of things. This would be the new retrosynthetic analysis. And so could you fragment these types of molecules? And so Joan, again, went to the lab and made a model system. And he was able to show that, sure enough, you could make this compound activate the tertiary alcohols immediately, knock out the acetate, and this would just pop right open at room temperature and 95% yield. Now that's the kind of reaction that you want to use in the last part of the synthesis, not 1,2-dichlorobenzene at reflux at some point on a really complex molecule that you've made. Now, people have different ideas about the model system. Some don't like to do them at all. In our group, we do them frequently. And here's just an interesting example of why. In thinking about how to put this model system together, John began teaching himself a lot about radical ring closing reactions. And that's going to, again, start to play a key role as the synthesis progresses. So students start learning new types of chemistry when they're putting the model system together. It's the first time they start really thinking deeply about how this molecule is going together and whether it's a good approach or not. And so that was an upshot of this model system study. So things were looking good for this fragmentation reaction that I showed you here, the retrosynthetic analysis model system looked good. Now, one of the things that I'll point out is that this is a retrosynthetic arrow. And usually when you're doing retrosynthesis, the structure on the right-hand side looks like it should be easier to make than the structure on the left. And when that doesn't happen, there should be little warning bells that go off and say, I don't think this is the best idea in the world. And so Jan can tell you that this really isn't the best idea in the world. I think his committee suffered through at least one chapter, if not two, about failed approaches of how to put something like this together in order to do the synthesis. That just was not going to happen. So another change needed to be made. You had a cool idea, but constructing the substrate for that just wasn't going to work out. And so realized, well, these two parts of the molecule are similarly functionalized in the product. He could really do a fragmentation on just a regioisomer of that. And that would lead back to this sort of fragmentation substrate, where at the core there was a 2,2,2 bicyclic system instead of this 2,2,1 bicyclic system. And then what changed is that we started doing SciFinder searches on those sorts of ring systems. How do people make those intermediates, these isotwistanes, what was out there that we could begin with. And we started to find some interesting chemistry. I'm going to show you an example of that in a minute, but just point out the fact that Jon built another model system that fragments no problem. So what was Jon finding in the literature? He was finding some interesting aryl oxidation Diels-Alder chemistry that was leading pretty rapidly to these types of ring systems. And when you look at the structures that I've been drawing, it's not that obvious. But if I redraw the molecule here on the right, show it here again, and simply redraw it there, just in a different orientation. And then you compare that to the intermediate that we hope to make in this retrosynthetic analysis. You can see how this molecule starts mapping onto these intermediates. So aryl oxidation Diels-Alder chemistry started to pique our interest in terms of the way to approach this. And so we thought, all right, now we have some things gelling. We have a nice fragmentation reaction we can try to use. We have a good way to maybe construct the core structure. Let's get to work on this. And so now I lay out a whole retrosynthetic analysis for this plan. We would introduce some maleic anhydride late from vinylic acid, or we make triplate and introduce the other. We do the fragmentation on this isotwistane like core structure. That compound will come from this intermediate. You can see what Jon's incorporating in the construction of this compound is radical ring closing chemistry here in this tandem radical cascade reaction that's going to be used to zip up this isotwistane. One thing that's happening in this reaction as well is this is where that all carbon quaternary center is being generated, and the stereo control is just coming from the ring system in the substrate. So it's a nice way to control that quaternary center, we thought, as well. This compound is going to come just from removal of the opening the lactone, removing that by an aldol reaction. You'll see how that goes in the forward sense. And here is the aryl oxidation Diels-Alder reaction. So this looks great. We would make two major components, bring them together, and then carry the material forward. So we started to think about how to make these components. How do we construct the aromatic piece that we need? How do we construct this aliphatic part that's going to stitch in many of the carbon atoms in the molecule? And Jon came across a paper in the literature where this catechol is prepared. Just from this butane dione, you make the bis-2-methane ether, do a Diels-Alder reaction with dimethyl 7 dicarboxylate, get this intermediate, you can oxidize that. Catechol, really easy way to make it. And Jon's like, wow, there's a really easy way in the literature to make this. This is pretty close to that. It has an extra ester group here, but in fact, in the product, there's another ester group there as well. So let's just use this compound as the starting material. Okay? We'll have to do the fragmentation later in a little different way, but we'll work that out when we get there. So we start marching down this path because there's this element of convergency. Some of these seductresses that we have in this field, we get tough into doing things. And we want to get it as convergent as possible, so we put in the extra ester, and then we're going to go forward with that. That will be an improvement. And so that's what we did. We made this compound, no problem. We're going to incorporate that into this retrosynthetic analysis. Nothing else has really changed. Okay. So we need to make this component. And that starts from this dibromo alkene. Put in 2 acetylenes, just displacing twice, sodium acetylide. Alkylate one end of this molecule. That's not a good reaction. Statistical mixture, as you can imagine. And we don't have a spinning band distillation column anymore, Fred, so we can't really use those separated like we have to. But we try. Now, sodium amide will protect one side from reduction by deprotonating and reduce the other side of the chemical. And then hydroaluminate and iodate to make white iodide. Incorporate that in a Michael addition to this enone, which is known in the literature at the time. We capture that intermediate enolate as this TMS enolate, which allows us to capture that site-specific position of the bromine with respect to NES. So that's the side chain piece that we're going to need in all of its glory. So we have now this catechol. We've protected one of the alcohols. Here a little bit of cesium carbonate displaces the alpha bromide. This is ether. We have to do a protecting group swap. We're eventually going to want to do an aryl oxidation. And if we don't protect here, this phenol will close down on that ketone and hinder that aryl oxidation reaction. So we protect as the ethylene glycol acetal and deprotect the allyl group with palladium. That sets the stage for the aryl oxidation reaction. Just treat with palladium tetraacetate. Okay. This does aryl oxidation, introduces an acetate at this position, and then also it goes all the reaction takes place, much like the mechanism that I showed you on the earlier slide. And what I'll note is this reaction is fairly stereoselective. We get a 1-3 mixture of these 2 diastereomers. This is going to be Phomoidride C eventually. This is going to be Phomoidride D. This is the major isomers. This is where we decided that we're going to make Phomoidride D in this synthesis. It decided for us by the stereoselectivity of this Gibbs-Alder reaction. So this is now the compound I'm going to draw on the right-hand box. So that's where that notion came from. Okay, so the acetate is removed. TMS is introduced here. We needed a protecting group on this oxygen. It's not going to be labile to the base that we're using in this aldol reaction to generate the enolate from this beta amino ester. That does an aldol reaction to form the carbon-carbon bond at this position. Now we're getting into this radical cascade chemistry. So Johan had taught himself a lot about radical chemistry and the construction of his model systems. Stork had done some beautiful work in radical annihilation reactions using this very acetal. And the conditions that we use to introduce this acetal molecule are just taken from Stork and ones he uses on hindered alcohols. So to set the stage for all this, we take our aldol product and do the co-elimination. Remove the TMS protecting group that makes the exomethylene lactone. And we introduce Stork's acetal. And we treat that with tin hydride and AIBNs. We generate a radical here, and then 1, 2, 3, 4, 5 atoms away, a 5XO reaction. That forms a carbon-carbon bond and generates a new radical. And 1, 2, 3, 4, 5 atoms away, it makes another carbon-carbon bond, generating the 5-member ring here and a radical that's captured with a hydrogen atom with tin hydride. And that generates the product that's shown here, 56% yield. And now, in this particular set of reactions, you're getting a major byproduct. And there are only so many 56% yields you can take in the course of the synthesis before you're just spinning your wheels. And so, Johan was leaving the lab. A new graduate student, Ivor McDonald, was in the lab beginning to work on this project. And Ivor was taking this over, and it's like I got to slog through all Johan's chemistry, then I get to here, and we get a 56% yield. Let's try to improve this a little bit. And so Ivor started thinking about other ways of generating this radical. And I'm like, I never really kind of understood what difference is that going to make? You know, if you're going to make the same reactive intermediate, aren't you going to get the same product? And so there's another piece of advice kind of to live by. This was via Jerry Burson, upstairs here from us. And Jerry recalled to us that one time Woodward had told him that, you know, faced with a decision based solely upon hypothetical arguments, consider all reactions not to perform an experiment and disregard them. So the bottom line is, just because you think this is kind of a nutty idea, maybe it's not going to work, by all means, if you have the starting materials, the reagents, take the time, set the experiment up, and see what happens. I mean, really think about it after all. The more interesting reactions that you run are the ones that you don't know whether or not they're going to work or not. Everything seems obvious, the likely thing is going to work, and you're not going to have anything to find. And so I wasn't quite sure that fiber was going to get any traction by changing the conditions, but he went ahead and did it. He put samarium diiodide in the reaction to try to initiate that radical reaction by removing the bromide, the bromine group. And lo and behold, now he gets 97% yield of the right product. What in the world is going on? And so it turns out that what Ivor had done inadvertently, we didn't really think about this at the time, was change the way this reaction was working. He was reducing the Mali, introducing electrons here. And now this ring closing reaction was going from the top down, taking advantage of the natural polarity of this carbon-carbon double bond, leading to an anion intermediate here that expresses the bromide resistance acetal. Great result. So it allowed Ivor to begin moving more material through this synthesis, which he proceeded to do. So he had his material in hand here. He now had to work out conditions for fragmenting this molecule. It's kind of a different substrate than Young's model system chemistry was. But he had to access this tertiary alcohol in any event. And we did that by treating with 1,3-propane dithiol, which opens this acetal to the dithioacetal and exchanges the acetal down below to the dithioacetal. Ivor introduced a xanthate and then treats this with samarium diiodide. The hope was that this would generate an anion that would fragment and generate an ester enolate. This reaction didn't work. And in thinking about it, we thought, well, maybe there's a problem with this lactone, this carbonyl, making this a good leaving group. It doesn't seem like it's lined up to interfere, but what the heck. Let's look at something that doesn't have this lactone in place. And so we went back to the beginning here, and before we put on the xanthate, we reduced the lactone to the lactol by treating with dival. And now we introduce a xanthate at this position and a xanthate at this position, and we knock off the one that's at the acetal by treating with phosphoric acid. And so we end up with a xanthate here, alcohol here, and now when we treat with samarium diiodide, this molecule fragment. Okay, so things are looking pretty good at this point. This is where we are. This is where we want to be. Ivor just needs to deprotect the diphenyl and oxidize, deprotect down below, make the ketone, remove the test and oxidize, and introduce the double bond. So, a little phenylidide, diacetate, or the trifluoroacetate, we can use to swap out the thioacetals from the methylacetals and then oxidize with Jones reagent. Oxidizes this to the acid, acetal falls off, test falls off, oxidizes the lactone. Things are good. Ivor has a job at BMS, and he's still working there. It's time for him to start leaving. Barry Twinner joins the group. Barry, this great project, we're almost all the way to the end. So you can come to Colorado with me and finish it. And so then here's Barry's thesis. So that was a bummer. Very. So it's kind of like the productivity in my lab too. It's arrow. So no good. I'll tell you more about Barry in a minute. We had to move on. So Barry did finish his thesis and got a PhD working with Sun Chemical now, South Carolina. And we were kind of gratified to find a few little years later that here was Derek Clive again, made this compound. He couldn't put the double bond in either, so it's like it wasn't Barry. It was just this molecule was not going to cooperate. It comes time to introduce it into analysis. But we had to do something different. We've gotten all the way to the end of the synthesis. And believe me, when you have a graduate student's thesis that's like this, trying to convince another graduate student to work on the project at that point is just not going to happen. You have to wait at that point for some unsuspecting postdoc who doesn't really know the history of this project and say, have I got a project for you? Graham Murphy from Alberta. Okay. Come into the lab, just ignore this big red X here at the very end of the retrosynthetic analysis that we worked through. Okay, so we had some ideas. We needed to change this. We weren't going to be able to convert this this diester up to lead hydrogen. And in the literature, other syntheses have been completed where that ester was introduced late, kind of like the way we had originally planned to do it, from enol triflate, incorporating carbonyl group of palladium, and So let's just go back to some of these original ideas we had. In fact, we were a little bit worried about this scheme. As it turned out, it was a good thing to worry about. And Dave Spiegel in my lab had been working on alternative fragmentation strategies that were exploring ideas just like this. So there's a little bit of background work for Graham Murphy to start working with. But the retrosynthetic analysis changed, and it changed back to kind of the original idea that we had, where we didn't have that ester group here anymore. And so that would lead us back to an intermediate, where we're doing a fragmentation, much like the ones that Johan had explored in his model studies, and then doing a CO insertion. I'll note that this CO insertion is on a regioisomer of those compounds that had been in the literature. So we were hopeful that this would still work fine. So we went forward in this synthesis shown here. We started a little bit of different starting material. I'm just going to sum up a lot of work. We get to this compound in 8 steps. We do the aryl oxidation Diels-Alder reaction. Also note that Graham was not willing to make the side chain piece just yet. He wasn't that committed. And so he's doing a model system study here. He gets to this intermediate, so this is the Diels-Alder product. He can carry through to the substrate that we want to use for the radical cascade reaction. He did that reaction with tin hydride, and sure enough, the cyclization took place and good enough yield to go forward with. Exposes this alcohol, again, by making the dithiene this position, and produces a mesylate, just like Johan had done in his model system studies. And that gave us this product. And we deprotect at that point the benzyl group here, and the hope was that now we would be able to fragment this molecule. And I just point out some crystal structures here. We couldn't get this fragmentation reaction to work. And one of the interesting things to note is that we went into this reaction with one stereochemistry of the ester, which came out with the other. So that was a little bit curious, but we tried treating with base, and this reaction didn't work. And one of the reasons we were looking at the crystal structure is that we were concerned about the problem. And the problem was, how did this stereocenter rise, and we think that it's doing a retroaldol reaction. So one of these obvious, it's like, oh, don't you forget when you miss a beta elimination in a synthetic plane, right? You overlook a retroaldol reaction, which was kind of a silly idea. We're trying to use this fragment here, this retroaldol reaction. Jumps in, and that's how this. So this was a bad idea, the second generation approach that Graham was taking. We kind of established that the fragmentation would work. We reduced that ester and shut down the retroaldol reaction. The fragmentation was fine. Then we started, okay, let's back up one more step. We took out one carbon atom and keep losing convergency. Well, we've already, sacrificed convergency. Let's just do it one more time and take out that ester entirely and go back to the beginning and bring through this unfunctionalized substrate and see if we can go forward with that. So now this is like the third generation approach. You've seen 3 graduate students and 1 red X with that arrow, 1 postdoc, quite a bit of work, and a red X in fragmentation. And so what was happening, we were just changing those substrates, kind of got seduced into introducing that ester for the sake of convergency. That messed up the first approach. This looked better, but that wouldn't have worked anyway. The retroaldol reaction stepped in. So now we're just going to rid ourselves of that problem by removing that ester entirely and start with an even simpler aromatic story. So now the retrosynthetic analysis looks pretty much the same. Again, really the only thing that's changing is the group that we're attaching to this side chain. And so we'll go forward with all the same chemistry. Let me show you how that's working out. So here's the starting material. We introduce a nosyl group. This is not selective. We introduce allo group, and then we filter and wash, and we can separate these 2 isomers. And so this is a 50% yield of 5-to-1 mixture of this compound, but there's no substitute. Not the greatest way to start, but cheap starting materials, even chemistry review, we load this material. MCPB8 is a viral oxidation to introduce the aryl oxygen. We use the same side chain piece, cesium carbonate, to introduce the aryl group. Protect, to stop that ring closing reaction. Protect the allo group as before. Here, lead tetraacetate. That does the aryl oxidation Diels-Alder reaction. Again, the major diastereomer is the one for Phomoidride D, so everything's pretty much the same. And I'll note that quite a lot of work went into figuring out we have to have somewhat of an electron withdrawing group on this ring to make that Diels-Alder reaction work. That nosyl was really important. After the lead tetraacetate reaction, we work up with just throwing in silica gel. The acetate falls off, and then we can introduce the chemist group. And setting the stage for this aldol reaction, same aldol reaction we used in our first generation approach. We remove the nosyl group with thiophenol. Do the co-elimination, cyclize the exomethylene lactone. Introduce the bromoacetal. Diesel chloride goes on the tertiary alcohol to set the stage for the fragmentation reaction, which happens when we remove that acetate with KOH. So acetate Now there was a challenge. One of the things was that this gave us a ring open product down here, and we had to close that back up with 3x3 methyl chloride. But which side of this ketone is going to react? We wanted to introduce an acyl group on the left-hand side using Mander's reaction. And we thought, well, this has a quat center, this is a neopentyl, maybe we could get lucky and introduce the group over here. It turns out that we could do that. I don't think I showed that here. But it turns out this, we can equilibrate the enolate to the thermodynamic. Just luck, fortunate, had no planning, just try this and see what happens. If you treat this under kinetic conditions, the predominant part is acylation on the right-hand side, and you get some O acylation. If you let this equilibrate for a while, we can get the Mander's reaction on the proper side of this molecule. So that was lucky for us. And going forward, then, we just treat and make enol triflate and palladium acetate with CO over pressure. And that will close to give palladium hydride. So this is where we are. And at this point, I'm at least happy to say that we have nearly 100 milligrams of this intermediate. It's up to Aaron Betterman and Joyce Bloom. Aaron's a graduate student, so actually this started looking better now. So a graduate student was willing to work on the project. Aaron has to deprotect and oxidize. So that's where we are. So for the first time, I'm feeling comfortable that maybe we could finish this synthesis. But it's never over until it's over. So we'll hold out and see what happens. So here's what I told you. First generation failed, very late stage, introducing the maleic anhydride. Way ahead of schedule. That's okay. All right, maleic anhydride. Then early on, or then the second generation approach failed in the fragmentation reaction because of a Loretto-Gallo reaction. And here, this third generation approach where we kind of minimize the convergency when it comes to introducing this maleic anhydride. But if you think about the number of steps it costs us to put that in, it's only a couple. And trying to fix the other approaches would have been much worse than that. So this turned out to be the best approach to take if we're going to take this approach in terms of introducing that maleic anhydride. So I'll bring you back to this quote. That's where that synthesis stands. That Woodward had made at the Welch Foundation. At the very end, it was rather the important things are those that you find out in the course of attempting to reach the objective. I haven't told you some of the things that we found out of this. In fact, the predominant amount of David Spiegel's career in the lab was to explore a new deoxygenation method using water as the hydrogen absolute. It was a cool thing that came out of this project. There's some interesting things that came out of the project in terms of samarium diiodide. But always when you do a synthesis, you can never really count on new chemistry coming out of the synthesis. It's nice that if it does. But I think the one thing you can always count on is that they're good students. You learn an awful lot in the course of this. So in addition just to the chemistry that you're learning along the way, the people that go through these projects are always something that you can count on that's good that's coming out of this. So I'll show you a few pictures. So this is Joan. He started the project in 1997, 1998. Ira McDonald took the project over. So Joan went on to Cornell, and he's now at the University of Arizona. Ira went to Wallingford at the DMS in Wallingford right after his PhD, and he's still there. David, as you've heard referred to maybe earlier today, but he's went from my group to postdoc with Stuart Schreiber, and he's now on faculty here at Yale. And this is Barry. His thesis was that X, but he maintained a positive attitude, throughout the whole thing. And that's always great. And struggling through this, faced with adversity, Barry was always this kind of, happy. One of the funny things, Barry was from Missouri. And as Mike, or as Fred said, I was born in Iowa. And then, one Italian group meeting, Barry's like, oh, you know what people from Missouri say about people from Iowa? Iowa stands for idiots out wandering around. Like, well, Barry, from the looks of your thesis, we're out wandering around together. So, better like that. So there are a few postdocs that worked on this project. Tatsuya Shirahara, he was contemporary with Ira and Dave. And Naoto Hama, contemporary with Barry, he was at CSU with me. Tatsuya is at the Kitasato University in Japan now on the faculty. Hama is in Tohoku University on the faculty. And Graham Murphy was the postdoc that picked up the project at CSU and then started doing the oxygen-based fragmentation. Graham's on the faculty at Waterloo. The two current students, a graduate student, Aaron Betterman, and Joyce Bloom, a postdoc from Mike Pichet's group, I said, I'm giving this talk, I need pictures, we have a good rapport, in the group with my students, so they sent me their pictures. This is Aaron. This is Joyce. They wanted me to know what they looked like when we started this project. So Aaron was 10, and so was Joyce, it turns out. Aaron was longer to finish his degree than it took Joyce. So they're contemporaries in terms of age. See, Aaron has a nice smile, a little goofy haircut. He likes airplanes. Joyce is interested in purple. Here they are today. See, Aaron has the same smile, same goofy haircut. He's the shave though now. And Joyce is still fascinated with curves. They glows all the time. Just terrific students, and they've been a pleasure to work with too. And I think that they have a shot here for the first time to finish the project that these folks started. So with that, we just thank a few people besides the students who worked on the project. Baylor, the secret is a fund in Texas for cancer research, the Welch Foundation, the Uehara Foundation, JSPS, and Satoshi Omura, and the Kyoto Institute all funded Japanese postdocs over a period of time in my lab. NSERC funded grant, and we were able to get some funding from the NSF for this project as well. Fred mentioned we recently moved south, where I never thought we would be, but the lab facility there is beautiful. These are the 4 graduate students that moved with me. The group's doubled down in size since then with postdocs. It's a beautiful facility inside. There's actually a Starbucks right here, so I don't have to go outside and get my coffee. So they always say it's hot in Texas. Well, I don't know, because I just want to go outside and go to my office. It seems all air conditioned to me. So it's really been a pleasure to work there and with these students. Because again, it's a real honor to be here to honor Harry today. It made a tremendous impact on my life, not only being a super colleague here and setting the tone for this department while I was here, but opening doors for me everywhere that I turn in my career. You can always count on that. I'm really appreciative of that. I want to thank Fred and Mike for their efforts to organize it, Bruce as well, and also Pat Brodka for doing a lot of the logistics. And I want to say that many of you, if not all of you, should have got an email from me inviting you to contribute to a symposium in print in memory of Harry. You can come out and check even letters from early next year. And I have to say that the response has been tremendous. Everybody that writes a paper, that's told me they're going to write a paper, writes a paper. There are 200, 230 papers in this issue. It will be the biggest one. It had to be 2 issues, but we'll see. Of course, not everybody always turns them in, but nevertheless, the response, as you might imagine, has been tremendous. And just the email messages back touching and sharing into those with you today. But they were certainly all the same super great things. So thanks again for your attention.
Well, I'd like to thank the 3 speakers that we've heard from thus far, Bruce, Brian,